Okay, so we're going to try and solve this problem here. So we've got 6 questions. What's the probability of getting one question right? What's the probability? I know you know the answers, I've heard you say it already. What's the probability of getting one question right? So if we get the first question right, the probability of that is 1 out of 4. Let's say we get it right. If we get the second question right, what's the probability of that? 1 out of 4. So the combined probability of those two, how would we calculate that? If we wanted to get the first one right and then the second one right, 1 over 4 times 1 over 4. So we multiply it. Now we only want 2 questions right. We only want 2 questions right. What do we have to do to the next question? We have to get it wrong. So what's the probability for getting something wrong? So we need a 3 out of 4. And then how many questions do we need to get wrong? How many questions do we have to get wrong? 4. We have to get 4 questions wrong. So this is the probability of getting 1 question right, 1 question right, 4 questions wrong. And this can be simplified to 1 over 4 squared, 3 over 4 to the power of 4, like this. Is this the right answer?
No.
Why not? Well, we don't have to simplify it. Is this the right calculation that would give us the right answer? This is where it gets a little bit tricky. So what did I calculate? Which question did I get right? I got the first 2 questions right. Could I still get 6 by not getting the first 2 questions right?
No.
Yeah.
How?
Because
I could get the 3rd and 4th, the 5th and 6th, the 1st and 5th. How many different combinations are there? How many different combinations? If I need to get 2 from a total of 6, how many combinations are there? Did you do this last year in line 3? Combinations? How do we pick 2 from 6? Yeah? So what we want is, we want to pick 2 from 6. That's 15. That's 15. The combination number there is 15. There's 15 different ways to pick 2 from a total of 6 options. I'm not going to show you how we can go into this. Do you want me to show you how this sort of works? I'll show you. So let's say the first 2 are correct and the next ones are false. Let's say I leave this number static and I move this one this way. I could get the 1st and 2nd, 1st and 3rd, 1st and 4th, 1st and 5th, 1st and 6th. How many different ways can I move the second one across here? How many different positions can this T be in? It could be in 1, 2, 3, 4, 5 different positions. So then I do the same thing again, but I insist that the first one is false. I'm always going to have the second one as true, the first one as false, and then I can move this into how many different positions? No? How many different positions can the second one be in? It can be in 4 different positions. It can't be in the first one. It can't be in the first one. It can't go here because I've already got the combination with the first and second one calculated here. I have to find new combinations. So it can't go in the first place. So if I have one definitely in the second, I can have one in the 3rd, 4th, 5th, and 6th. So then I've calculated all the ones where the first 2 have trues in them. So we go there like this. This one has to stay in the same position, and this one can move. It can move into these two locations. So there's going to be 3 different ways here at this point. So then I've calculated all the ones where there's been a true in the first, the second, and the third. So I have to have those as false. I'm going to have a true here. This one has to stay static. This one can move into 2 possibilities. And then the last one, it can't move. I've got to have all of these false and these 2 as true. There's only 1 of these. Add that up, you get 15. 15 combinations. This will give us our answer of 0.297. This is how you make these types of calculations. We are not going to do that. We can use the calculator. There.
I did it.
Well, I'm going to do it. All right. So let's take the same question again and do it using the calculator.
The combinations are
5, 10, 15. Okay, so let's say we get this question. This is your exam style question that we might have to solve, and this is how we would notate it. So X is going to be our event. X is going to be our event. What does X do? X counts. So X counts the number of correct answers. So you always start an answer to this type of question with the phrase, X is the discrete random. You don't have to say X is the discrete random variable. You can just say X is the number of. So this type of question always starts with this exact phrase, which is why I've drawn it in black. X is the number of ... and then you have to fill in the ... So what is X the number of? Correct answers. So X is the number of correct answers. Every question like this, you must start with the phrase X is the number of, and then fill in whatever it is that you're counting. It'll also help you solve the question and think through the question. Then you need to say how X is distributed. So this says X is distributed binomially. It's a binomial distribution. X is distributed binomially. We have to have 2 factors that defines 2 parameters that define the binomial distribution. We have the standard formula. I'll put it up here. X is binomially distributed by n here. This is the formula. N is the number of trials. So how many times do we try and get a right answer? What's the probability of success? So we want the probability that the event X results in a 2. We want the probability that the event X results in a 2, meaning 2 correct answers. So your question should always look like this. This is the mathematical method of how it looks. I want to really see some good notations on these ones. You'll be losing points if you don't on your tests. So pull up your calculator in your hand now. Get your calculator in your hand. They can look slightly different in the locations on the CAS calculator, but what we press is we press menu, probability, and then the distribution. So menu 5, 5, and here we'll find the different probability distributions. We want binomial PDF, A. We want A. So you can press A on your keyboard for this one, it'll come straight to it. We have to say how many trials, 6. We have to say what the probability of success is, 1/4. and what is the x value that we want? We want x equal to 2. Type these in, and then press OK. We get 0.297. 2. Let's go back and see if it gets the same answer as this one. So this calculation we can do on the calculator. Are we watching? This calculator we can do on the calculation. We don't need to do it this way, but your probability will get the combination number. We have 6 options and we need to pick 2 correct answers. So NCR 62 times, and then a bracket. We want 1 over 4 to the power of 2 times bracket 3 over 4 to the power of 4. And we should get the same answer with the binomial as with the calculation. These are the same numbers. We just put my document settings now. And there. Document settings. I'm going to put it into float 3 for this next bit. And document settings. There we go. All right. So let's have a look at the binomial distribution. So for this question, we have a few more bits and pieces. We have to find when x is equal to 2, when it's less than or equal to 2, when it's less than 2, when it's between 3 and 6. Let's have a look at how these answers go. So what we need to say to begin with is x is the number of, what is x the number of?
Correct answer.
Correct answers.
So why do you have to write it down? It says it in the question.
You have to write it down.
Yeah, it's the method point. It doesn't always say it. It doesn't always say it so clearly in the question. This is an easy introductory question. Usually, it's less opaque in the question. What I tend to find best is if you always do everything the same way, you don't forget to do things that you need to do. So I always do it in the same way, if I can. There's certain really tricky procedures that if I drill them in, we do it the same way every time, we always get success. So here's our method. X is binomially distributed. So we can get the whole probability distribution. So this looks like the discrete random probability distributions we were looking at last week. And we can get that entirely from the calculator for this one. So if we repeat what we did on the calculator last time, but we leave out the x value, if we say menu, probability distributions, probability normal PDF 6, 1 over 4, and leave the x value empty, you'll get the whole probability distribution. It looks like this. So we have 0.178, 0.35, 0.356, 0.27, 0.297, 0.132, and then they start to get really small, 0.033, 0.004, and this one's even smaller. So if I just scroll across there on that one, it's 0.00024. If I add all of these numbers up, what do I get? If I add all of these numbers up, what do I get? We get 1. You can see roughly here that they're going to add up to 1, hopefully. So the 4, 5, and 6, that's almost nothing. That's a 0. So you've got just less than 2, just more than. So the first two will add together to about 5. The next ones will add together to give about 9, and then you add the last bit up, and you'll get to a whole. What is the probability? So answering each question. What is the probability that the discrete random variable, the number of correct answers, is equal to 2? That's this one, 0.297. B. What is the probability that the number of correct answers is less than or equal to 2? What we need here is you need this. You need this. So these are the probabilities where it's less than or equal to 2. So we have to add them all up. We have to add them together. So we could add them up, 0.178 plus 0.356 plus 0.297. The calculator will do it for us directly. We turn back to the calculator and we do probability distributions, and then you scroll down. This doesn't scroll down well on mine. Menu, probability distributions, scrolling down. You'll notice B, normal CDF. So to remember the difference between PDF and CDF, P is when you want a particular number. C is when you want a collection of numbers, a cumulative probability. So if you're collecting the numbers together, that's C. Here we have the cumulative process of 0, 1, 2, and 3. So it's the cumulative probability distribution. If you're collecting 3 numbers together, you use the CDF. So we want binomial CDF. We got 6 trials. Our probability of success is 1/4. Our lower bound is going to be 0, and our upper bound is going to be 2. And it will add those up for us and give us the answer. Oops, maybe I typed something wrong. Let's try it again. Yeah, 0.3. 0.831. What is the probability that it is less than 2?
You just put the 0 in the, like 0.178.
So let's take care with these ones. We want x to be less than 2. This is equal to the probability that x is less than or equal to 1. With a binomial distribution, we cannot calculate less than. So we have to calculate less than or equal. We have to do less than or equal. So shift it across. So you can shift less than 2 to be equal to be less than or equal to 1. You can't do this with normal math. Why not? Discuss with the person next to you. Why can't you do this normally? You can do it here in this situation, but you couldn't do it if you were looking at a graph. We're looking at a graph. Less than 2 is not the same as less than or equal to 1 on a graph. Why? What's the difference here? Okay. So is it possible to get 1.9 questions right? Is it possible to get 1.8 questions right? Is it possible to get 2 questions right?
Yes.
So less than 2, the next number less than 2 is 1. We don't have the numbers between 1 and 2. This is not a continuous function. This is not continuous. It's discrete. We only have the answers 1 and 2. So all of the numbers less than 2 are the numbers 1 and downwards. There's no 1.9s, 1.8s. So we can convert with a discrete probability distribution, x is less than 2 to being less than or equal to 1. These are the same things. That's because it's discrete, because there are no values between 1 and 2. This is not the same for continuous data, like on a graph, when you're looking on a number line, when you're looking at numbers. So we can calculate that now on our calculator. I'll just scroll up and take this one, and you can start to learn what the syntax is, the number of trials, the probability of success, the lower bound and the upper bound. So I just need to change the upper bound to 1 on that one, and I get 0.534. Have a go at calculating D for yourself at this point. Let me know what the answer is. Have a go at calculating D. Sorry, you need to get your ass.
What you got? You put 6, 1 over 4, 3, 6. So it's 10.1. Well, you work on 6. They're both 7.
Okay, let's have a look at the answer. You should get 0.196, is it? 169. That's because this probability is the same as the probability of going from 3 up to and including 5. This is what we have to do on the calculator. So I'll just take this. This wants to be 5. 3 to 5. 0.196. 169. Ooh, we've done all of that. Okay. So have a go at this question. Have a go at this question for yourself. I'll come around and assess how you've done. Let's have a look at this. So with this question, too many of you started with your calculator. You need to start by saying what x is. It will help you get your head around the question. You've got to really figure out, always start by saying what x is. X is always the number of something. What is x the number of? X is the number of times 5 or 6 are rolled. Writing this sentence down is going to help you think as you solve the problem. It's going to help you. So x is the number of times that a 5 or a 6 is rolled. How is x distributed? Well, it's distributed binomially. What is the problem? How many trials are there? 10. What's the probability of success? We want a 5 or a 6 out of how many?
6.
So we want 2 over 6. The probability of success is 2 over 6 or 1 over 3. And then lastly, we want the probability that x is greater or equal to 3. That's the probability that x is between 3 and 10. We want the probability that x is greater than 3. That's the probability that x is between 3 and 10. So then we can just do it on our calculator now. Menu, probability, distributions. We want binomial CDF. We want to collect a few values together. We got 10 trials. Our probability of success is 1 over 3. Our lower bound is 3. Our upper bound is 10. Our answer is 0.701. Matt?
2 over 6.
You can do 2 over 6 or 1 over 3. It's the same.
Yeah, why did we do 2 over 6?
Because you want to get a 5 or a 6, and there are 6 sides on the dice. So because it's symmetrical, you've got one chance of getting a 5 out of 6, one chance of getting a 6 out of 6. The total probability is 2 out of 6. All right. One of the trickiest things is you'll get questions and it won't sort of guide you as much as today's lesson. Well, today, you always know it's going to be binomially distributed because I'm doing a lesson on binomial distribution. I'm not throwing problems that aren't. On a test, you might not know it's binomially distributed. Some of the harder questions are ones that start off normally distributed, and then they ask a question towards the end, and that's a binomial distribution because they're starting to count. When they trick you and they go halfway through for some of these longer questions, it gets tricky. So, it's essential for you to be able to understand the context where a problem is going to be binomially distributed. So to determine this, ask yourself a couple of questions. What is the random variable counting? Are we counting something? Is it the number? Are we counting how many times something happens? So if it's x is the number of, and you're counting it, a good chance it's binomially distributed. The trials need to be independent of each other, which means you have a constant probability of success. So let's say for instance, you're taking marbles out of a bag. You're taking marbles out of the bag without replacement, it can't be binomially distributed because the probability inside the bag is constantly changing. It has to be like when you're rolling a dice, you roll one die, you get a 1. You roll it again, you can still get a 1. It never changes the probability based on what you've just got. So the trials should be independent of each other, which means that knowing what happens in one trial doesn't change the probabilities in any other. You also have to have a fixed number of trials. You can't have a binomial distribution where you keep going until something occurs. So you keep doing it until you get a 6. Okay? You can't have that. It has to be a fixed number of trials. It also has to have a constant probability of success. So the things you should look for is, are you counting something? Are there a fixed number of trials? Is there a constant probability of success? Then it's binomially distributed. What you need to have in a binomial distribution is you need to have 2 possibilities, success and failure. Success and failure. So a lot of things can be set up like that. So if you're looking at the probability of getting a 6 on a dice, you might think, well, there's 6 probabilities. I can get 1, 2, 3, 4, 5, 6, and so on. But you can't. You can get a 6, or you can not get a 6. And then it becomes binomial. When you can separate it into 2 probabilities like that, success and failure, it's binomial. All right, have a go at this question for yourself now. Pause the video a minute, 2. Okay, so the first one, we've got coin being tossed. So this one is binomially distributed. So for A, we say that it tells us in the question. I'll just skip that. We've got A is binomially distributed. What is the probability of success in the number of trials? We've got 7 trials, and the probability of success is 0.36. 1 minus 0.74, no, 26. You can type it in like this on your calculator. You can type it in like this and it'll do the calculation. And then we want the probability that A is equal to 5. So this should give us menu probability distributions. We want a particular value this time. 7 trials, 1 minus 0.74, and we want it to be 5. 0.014. B is not binomially distributed. C. Is this one binomially distributed? Notice that there is replacement, so we can say that C is binomially distributed. C is distributed binomially. How many times do we repeat it? What's the number of trials? 12. We repeat it 12 times. What is the probability of success? So we've got 7 yellows out of total of 18. So 7 out of 18. And we want the probability that C is less than or equal to 6. So menu probability distributions. We want a cumulative one. We've got 12 trials, 7 out of 18. Oops. 7 out of 18. Our lower bound we want 0, and our upper bound we want to be 6. And we get 0.861. D. So with this lottery one, we have a fixed probability of success, but we don't have a fixed number of trials. So it is not binary. Okay, we've got 5 minutes left. Have a go at this last question. Let's see if we get a little bit quicker here on this one now.
When it says exactly, do you have to mean like in a row or right? Any.
What is X? Always start by defining what X is. X is the number of what?
The number of times the coin face
So X is the number of heads. So this would be that you get 3 heads, exactly 3. It's just a particular part of the probability distribution.
Okay, this is the 8. This is B.
Yeah.
Strike 861.
Like, if you slow, I need more.
I get it. Wait, what?
Oh, she was thinking about the
Okay, so no more than 4 heads. No more than 4 heads. That means we want 4 or less. What do we get as the probability for that one? That's right, 0.891. And C, at least 3 heads and fewer than 6. So this time we want the probability that it is between 3 and 6 like this. So we want the probability up to 5. What do we get? .641. All right, we're finished there for today. I would not fail to do this exercise. Make sure you do this exercise. Exercise 7K, it's a very important one. We're going to have a minor next week.